Hey, my name is Lucas, and this is my large ISP project, The Helping Hand. This project's meant to enable spinal cord patients to be able to move their fingers again and be able to grab things to really improve their autonomy. First, I'll go over the many parts of the main PCB, which goes to the top of your hand, and how they work together to kind of control the helping hand. I'll then go over the touch sensor that goes in the palm of your hand and the exoskeletons on each finger. On the main PCB, it's mounted at the top of your hand, and on it right here in the center is an AT Mega, which is kind of the brains of the operation. It tells everything else what to do based on input data. The AT Mega needs a couple of other things to operate. You can see directly to its left of this little 16 megahertz crystal with two capacitors that tie to ground. This is the timing of the chip. The AT Mega does have an internal 8 megahertz clock, but 8 is obviously less than 16, so the clock would operate much slower, and this internal clock is much less accurate than this external one. Also, you can see here the bottom left of this PCB, female USB mini type B port. This is what I use to plug into my computer to program the actual AT Mega. To do this though, it can't go directly to the AT Mega. It needs to go through this chip, which is directly to the right of this port. This is a CH340N, which is a USB to serial converter. And this converts the data from your computer to data that the AT Mega can understand. It transmits this data through the TX and RX pins on the AT Mega. On the very far right edge of this PCB is also the reset switch for the AT Mega. This will reset if anything needs to go wrong, and we'll just completely wipe it. Additionally, there is the on and off switch right below it. This just turns the entire thing on and off, and directly before that is a little status LED. It's red, so if it turns on, that means the PCB is on, and if it's off, it means PCB is off or not getting power. To power each motor, the AT Mega really outputs 3 different types of data. Each motor is powered by a voltage 8 bridge, which you can see up on screen, and it's really described more in detail in the DER report. The voltage 8 bridge needs 4 pieces of data to determine if its 4 MOSFETs are activated or disabled. That's where the AT Mega comes in. It provides the data for all the N-channel MOSFETs and P-channel MOSFETs, and it does this through 3 595 shift registers, which are tied together in series. The data goes directly into the N-channel MOSFETs. If its output is 1, it's enabled. If its output is 0, it's disabled. The P-channel MOSFETs work a bit differently. They're combined with 5 PWM signals that also come from the AT Mega. So each 595 P-channel output and PWM are combined in NAND gates. P-channel MOSFETs are activated if they receive a low or a 0 on their gate pin, as opposed to the 1 or high on the N-channel MOSFETs gate pin. In the NAND truth table right here, it shows that only if both inputs are 1s, it outputs a 0. This means that the 595 has to tell the MOSFET to turn on, and it's periodically turned on and off by the oscillating PWM signal, and this is how each motor's direction is controlled and how their speed is controlled. The final main chip on this upper PCB is the 5 current sensors. They detect the current from each motor, and this is really for safety reasons, but also a practical purpose. First, let's say your finger encounters like a solid wall or obstruction. You might not be able to pull your hand away in time. So if the motor just kept on pushing and pushing, it could break the mechanism, but also hurt the user. So this would really prevent that. If the current of the motor goes over a certain limit, automatically stops every single motor. Second, once your hand is grasped around something, you don't want to keep on pushing. You can either crush the object or crush your hand, really. So once your hand is grasped around an object, the current increases, and this will tell the AT Mega to stop the motors. The way this current sensor works is it's a Hall effect based sensor, so it can measure both AC and DC current. Since it's Hall effect, it means that current flow through a conductor generates a magnetic field proportional to the current. As the ACS 712 Hall effect sensor detects this magnetic field, it converts it into voltage, then outputs that measured voltage to the AT Mega, and which determines what to do with this data. In the code, I've set it so that if this voltage is over a certain limit, it will automatically stop the motors. On the very left of the PCB is this little white port. You can actually plug this ribbon cable into it, which goes directly to the touch sensor. Touch sensor is honestly a really simple PCB. It's just 2 copper pads placed on top of each other on different layers, obviously. The only part on this actual thing is the connection to connect it back to the main PCB. Directly below that port, on the main PCB, you can see the FDC 1004. It's a little tiny black square, but it's honestly the most complicated chip in this entire project. In this case, we're only using 2 of the pins, the CIN1 and SHIELD1. These are connected to the 2 copper pads on the touch sensor. And the way this chip actually works is by creating a magnetic field between the 2 pads in this case. When something enters this magnetic field, like an object or something you want to grab, the sensor detects this change and sends the data to the ATmega through I2C. The FDC 1004 can be used without the shield, but it's used as a reference point, so the entire mechanism is not accidentally triggered by small changes that really aren't meant to be detected, like atmospheric or temperature changes. This chip is so precise that it can detect down to 1 femtofarad. The final kind of part of this project is the finger exoskeleton. On the screen is the Fusion 360 view of just one finger. You can see here it's split into 3 different parts for each different section of your finger. The holes on the side are a space for bearings and for each section to rotate independently. There's also this brace here, and that goes just in front of the main PCB. There's 4 hooks on its top, which are very similar to the ones in the final section of the finger. The spring stretches between these 2 hooks, and that's the force that repels the motor. It's what keeps the user's fingers open and opens their fingers once they're done grabbing something. Here's an example of me with it on. It's important to note that this doesn't actually fit me. It's a bit too small. It was made for my mom, so her fingers are much smaller than mine. But you can still see here that the spring, when it's completely open, your hand's completely open, it's fully tensioned. There's no tension on it. But when your hand is curled, there is tension on it, and the spring is trying to pull it back. So when the pressure of the motor is turned off, the spring will have its way, and your fingers will return back to normal. The Helping Hand project is a meaningful application of engineering that combines electronics, mechanics, and really human-centered design to create a device that empowers individuals with spinal cord injuries. This project exemplifies the potential of technology and really enhances autonomy and quality of life for spinal cord patients. That was my video on my large ISP, Helping Hand. Thanks for watching.